Pratima from Planet Physiology. In this video, you will learn about erythropoiesis. Before we begin with this topic, let us see a case scenario. A 50-year-old male visited physician with chief complaints of puffiness over the face and oliguria. He also complained of nausea, vomiting, persistent itchy skin and fatigue. History taking revealed he was diabetic and hypertensive for past 20 years. On clinical examination, blood pressure was 158 by 90 millimeters of mercury. There was yellowish tint to the skin and patient had mild paleness and peripheral edema. Laboratory investigations revealed hemoglobin was low, hematocrit also was low, blood indices were normal, serum urea, uric acid, creatinine and blood glucose levels were raised. So this is the case of renal failure. Now the question here is, why there is anemia in case of renal failure? So after studying this topic, you will definitely get this answer. So let us begin with this topic, and we shall study this topic under the headings definition, site of production, stages, regulation and clinical aspects. So what is erythropoiesis? Basically, this term is Greek and it has two parts, erythropoiesis. Erythro means red and poiesis means to make. Hence, erythropoiesis is defined as formation of mature red blood cells. Now let us study what are the various sites for erythropoiesis. First we will study the intrauterine sites for erythropoiesis. Even before the mother is aware of conception, blood formation has already started. During the first trimester of the pregnancy, red cells are formed from the mesoderm of the yolk sac, and hence this stage is known as mesoblastic stage. As blood vessels are not yet formed, this is also called as extravascular hemopoiesis. During the second trimester of the pregnancy, liver and spleen are the main sites for erythropoiesis, and so this is known as hepatic stage. During the third trimester, the predominant site for erythropoiesis is bone marrow, and therefore this is known as myeloid stage of erythropoiesis. Whenever blood cells are formed within bone marrow, it is called as medullary hemopoiesis. If any organ other than marrow synthesizes blood cells, it is known as extramedullary hemopoiesis, and the predominant extramedullary hemopoietic organs are liver and spleen. After birth, bone marrow is the main site for erythropoiesis and the red bone marrow that is responsible for formation of blood cells. Till the age of 5 years, all the bones contain red bone marrow, and therefore all the bones are capable of forming RBCs. As age advances, red marrow gets replaced with lipids and so becomes yellow marrow, and as a result they lose ability to form RBCs. So till the age of 20 years, all the membranous bones as well as the end portions of the long bones continue the process of erythropoiesis. After the age of 20 years, only membranous bones have capability of erythropoiesis. So let us summarize this erythropoiesis with the help of graphs. Shown here is the sites for erythropoiesis during the fetal stage, and this is the adult stage. During the first trimester, the predominant site is the mesoderm of the yolk sac, as shown by this blue color line. During the second trimester, the main sites are the liver and the spleen, and third trimester onwards, it will be the bone marrow. This violet color line represents the marrow within the long bones, and red color indicates marrow of the membranous bones as well as axial skeleton. After birth, till the age of 5 years, all the bones are producing RBCs, but after the age of 20, it is only the membranous bones which are engaged with the process of erythropoiesis. Now let us study the stages of erythropoiesis. The precursor cell that gives rise to all kinds of blood cells is known as pluripotent hematopoietic stem cell or just as hemopoietic stem cells. These are the largest cells in the marrow with a diameter of 20 microns. These cells mainly give rise to myeloid stem cells and lymphoid stem cells, and myeloid stem cells are precursors for RBCs, granulocytes as well as platelets. The next cell is colony forming unit spleen, and this is again the common precursor for RBCs, granulocytes as well as monocytes. Colony forming unit spleen further differentiates to form colony forming unit blast, which in turn differentiates to form colony forming unit erythrocytes. So these are committed stem cells for production of RBCs, and they give rise to Proerythroblast, which is the first cell that can be identified as belonging to RBC series. Now within the marrow, cells which give rise to RBCs are just 25% in number. These cells are called as erythroid lineage, whereas myeloid lineage which gives rise to WBCs occupies 75% of the population of precursor cells. So erythroid to myeloid ratio is 1:3. Now let us study about this proerythroblast, which is also called as pronormoblast. As I told earlier, this is the first cell that can be recognized as belonging to RBC series. Its diameter ranges between 15 to 20 microns. It has very big nucleus occupying almost 90% of the cell, and this nucleus contains 2 to 3 nucleoli, indicating that it undergoes active division. So mitosis will be shown. Cytoplasm is very scanty and basophilic in nature, and hemoglobin is absent in this stage. Next stage is early normoblast. Its diameter is 14 to 16 microns. Nucleus has reduced in size. Nucleoli are absent and chromatin material shows condensation. Amount of cytoplasm has slightly increased, but still it is basophilic and lacks hemoglobin, but it can actively undergo mitosis. Because the cytoplasm is basophilic in nature, the cell is also known as basophilic normoblast. Next stage is intermediate normoblast. Its diameter ranges between 10 to 14 microns. Nucleus has further reduced in size and chromatin also has condensed further. In this stage, hemoglobin starts appearing. Cytoplasm has increased in amount, and now the cytoplasm is polychromatophilic due to presence of hemoglobin, and as a result the cell is also known as polychromatophilic normoblast. This also can undergo mitosis. The next stage is late normoblast. Its diameter is 8 to 10 microns. Nucleus is now very small and called as pycnotic nucleus. It shows cartwheel appearance, and in later stages of this late normoblast, it is disintegrated or expelled out of the cell. So, later stage of this late normoblast will lack nucleus. Cytoplasm is now plenty and it is orthochromatic in nature due to increased concentration of hemoglobin, and this cell loses its ability of mitosis. So mitosis is absent. Late normoblast is also known as orthochromatic normoblast. It gives rise to reticulocyte. Reticulocytes are 7 to 8 microns in diameter. They lack nucleus, and remnants of RNAs can be seen in this cell whenever stained by supravital stains like crescel blue, and that is the reason it is called as reticulocytes. So these remnants, they appear like reticulum, so the name reticulocytes. Hemoglobin concentration has further increased and the cytoplasm is acidophilic in nature. Reticulocytes also cannot divide. These reticulocytes enter circulation by the process of diapedesis, and in 2 days they lose these basophilic remnants also and are converted to mature RBCs. Normal reticulocyte count in adult is 0.5 to 1%, whereas in case of newborns it is 2 to 6%. So estimation of this reticulocyte count can give you idea about rate of erythropoiesis. More the reticulocyte count, more is the rate of RBC production. So the last stage is mature RBC. Average diameter is 7.5 microns. It lacks nucleus. Cytoplasm is acidophilic and filled by hemoglobin. Mitosis is absent. So let us summarize the stages. The first cell that can be identified belonging to RBC series is Proerythroblast. Next is early normoblast. Both these cells show basophilic cytoplasm. Then is the intermediate normoblast. Hemoglobin first appears in this stage and cytoplasm shows orthochromatic nature. During early and intermediate normoblast, ribosome synthesis takes place and therefore cells are capable of cell division. In late normoblast, cytoplasm is totally acidophilic in nature. In the earlier stage, nucleus is highly condensed and in later stage, nucleus is absent. Next stage is reticulocyte. It shows the remnants of RNAs in the form of reticulum, and at this stage, cells leave bone marrow and enter circulation. Within next 2 days, it gets converted to mature RBCs. The total duration from proerythroblast to reticulocyte is 5 days and the next 2 days in the circulation, so total is 7 days. What changes take place during this formation of RBCs? First thing is reduction in the cell size. The volume of the cell reduces from 900 femtoliters to 95 femtoliters. So there is reduction in the cell size. Diameter of the nucleus gradually reduces and finally nucleus disappears from the cell. Also there is disappearance of all other cell organelles. Cells lose their mitotic ability. Hemoglobin synthesis begins and its concentration gradually increases. There is increase in the amount of cytoplasm and cytoplasm shows changes in its staining property from basophilic to eosinophilic. Formation of RBCs is very precisely regulated in such a way that rate of production is equal to rate of destruction. The number of RBCs in circulation is always maintained in such a way that they provide adequate tissue oxygenation and at the same time avoid sludging or thrombosis. There is something called as stem cell factor which is essential for self-renewal of hemopoietic stem cell, and this factor maintains constant proportion of stem cells in the marrow. All the regulatory factors for erythropoiesis can be divided into 3 gross categories: general factors, hemoglobinization factors and maturation factors. Let us see these factors one by one. So first is hypoxia. Decrease in partial pressure of oxygen at tissue level is called as hypoxia. It can occur at high altitude or due to anemia or due to cardiovascular or respiratory diseases. Any factor that causes hypoxia will ultimately release erythropoietin. So the next factor is erythropoietin. Erythropoietin is glycoprotein. It is discovered by Jacobson in 1957. Its molecular weight is 34,000 and 90% of the circulating erythropoietin is secreted by kidneys. Just 10% is from liver. This erythropoietin acts on colony forming unit erythrocytes and promotes their growth, differentiation, maturation as well as their release in circulation. Hypoxia due to any cause, like it can be due to decrease in RBC count or because of any cardiovascular or respiratory disease or due to high altitude. So hypoxia due to any cause will increase erythropoietin production, which will stimulate this precursor cell to differentiate, and as a result RBC production will be increased. Erythropoietin is circulated in free form as well as it is also combined to RBCs themselves. Whenever there is decreased RBC count, free form of erythropoietin will be raised, and as a result again this will stimulate the precursor cells. So increased production as well as increase in the free erythropoietin in the circulation, both are responsible for increase in RBC count. Once RBC production is increased, hypoxia will be relieved and erythropoietin concentration in the circulation will be reduced. So apart from hypoxia, the hormones like testosterone, catecholamines, thyroxine and prostaglandins also stimulate erythropoietin secretion, whereas estrogen inhibits secretion of erythropoietin. The third part under general factors is hormones. We have already seen erythropoietin. Apart from erythropoietin, other hormones required for erythropoiesis are androgens like testosterone, catecholamines, that is adrenaline and noradrenaline, prostaglandins, adrenocortical steroids, mainly the cortisol, then thyroxine, growth hormone and prolactin. All these hormones are necessary for RBC production. The diet containing first class proteins, vitamins and minerals is also necessary for erythropoiesis. Now let us see hemoglobinization factors. So these are the factors necessary for hemoglobin synthesis. The major hemoglobinization factor is iron. 65% of the total body iron is present in hemoglobin. So that is the reason iron is must for hemoglobin formation. Then minerals like copper, cobalt, magnesium, manganese are also necessary in the diet because they act as catalyst during the reactions of hemoglobin formation. Vitamin C acts as reducing agent and it helps in keeping iron in ferrous state. It also helps to remove iron from ferritin, which can be made available to the developing RBCs, and it is also necessary for keeping folic acid in its active form, that is tetrahydrofolate form. The last hemoglobinization factor is vitamin B6. It is coenzyme necessary for formation of protoporphyrin ring. Maturation factors are necessary for maturation of RBCs and they include vitamin B12 and folic acid. Both these factors are necessary for formation of the basic building block of DNA, that is thymidine triphosphate. Intrinsic factor or intrinsic factor of Castle is necessary for absorption of vitamin B12. Intrinsic factor is secreted from parietal cells in the gastric gland. It combines with vitamin B12 and protects it from action of hydrochloric acid in the stomach. It also helps in absorption of B12. So here we finish with the regulation of erythropoiesis. Let us study some clinical aspects associated with this erythropoiesis. If there is any deficiency of vitamin B12 and folic acid, there will be maturation failure anemia, and in this anemia RBCs will be bigger in size and this is called as megaloblastic anemia. If there is deficiency of intrinsic factor, again there will be maturation failure, but in this case anemia is called as pernicious anemia. Iron, as it is one of the important factor for hemoglobin synthesis, its deficiency will lead to iron deficiency anemia. If there is any bone marrow irradiation, say due to X-rays or gamma rays, stem cells will be destroyed and it will lead to aplastic anemia. There are certain toxic drugs like methotrexate which can destroy the stem cells and that can lead to anemia. And as we have seen in the beginning, if there is any chronic renal failure, it will lead to anemia because erythropoietin will not be available in sufficient quantity. Severe anemia will lead to hypoxia, which will demand more production of RBCs. And in that case, if bone marrow is not sufficient to produce enough RBCs, other organs like liver and spleen also can begin RBC production, and this is termed as extramedullary hemopoiesis, and these organs will increase in size, so they will be hepatosplenomegaly. Most of the time whenever this extramedullary hemopoiesis is taking place, blast cells will be present in circulation. Reticulocyte response is one of the ways by which patients' response to the treatment can be assessed. So this is all about erythropoiesis. Thank you. If you enjoy my sessions, press the like button and share it with your friends. If you haven't yet subscribed my channel, press the subscribe button. To get notifications about new releases, press bell icon. Thank you for watching and see you in the next video.